Okay, class, let's do my last question from the, at least from this email on some of the review here. It says here in this diagram, I guess it's number 17. I should mark that. Okay, 17. So in the diagram shown, a horizontal force F of 0.242 mgs. So I guess this would be listed as a percentage of the gravitational force. And y equal 1.25 times the width of the cabinet. Okay, so they don't really tell us what the width is or the force, but they give it in terms of multiples. Okay, to keep the cabinet stable, the force F2 must support blank percentage of the cabinet's weight. Now I'm a little confused here because they say force number 2, and it makes me think there should be another force here, but I think they want n number 2 in this diagram. So we've got two forces pushing up, and one is a normal force on the left leg, and another one is a normal force on the right leg. I'm going to go down that road. I think that's what they want here. Okay, and then they want it as a percentage. Okay, but the key to this problem, and like all these final exam ones, you got to stop and ask yourself, what kind of problem is this? Is this a kinematics problem? Is this a dynamics problem? Is this a work and energy problem? Is this a momentum problem? Is this a rotational problem? Is this a statics problem? And is it a fluids problem? I think those are the things you guys covered. And in this case, I think the answer is it's a statics problem. And statics included both translational and rotational. In fact, in our statics, we said the sum of all the forces have to be 0 to keep it stable, but also the sum of all the torques have to be 0. And so statics is actually a combination of translational and rotational. So it is partly rotational problem, but also partly just our kinematics or statics because it's not moving. Anyways, so we call these a static problem here. So let me start there with the idea that the sum of all the forces, and I'll just do the y direction, has to be 0. And normally I would say do a free body diagram for step number, 2. Step number 1 is got a good physical picture of what's going on. And step number 2 is draw a physical, the free body diagram. But I think in this case we can be okay not to necessarily draw a free body diagram because we have one given to us in the problem. And that also helps us with understanding the problem. So we just have a cabinet that's going to be stable, and there's going to be a certain amount of forces lifting up on the two legs, and looks like number 2 is bigger than number 1, and the question is, what percentage is that? So it's not a 50-50 split. There's more push based on this arrowhead, and I'm sure it's going to come out that way, but there's a bigger push here on the weight than on number 2 than number 1. Okay, so let's go ahead and like I said, we can run through the forces in the y direction. And it looks like I would have an N1 pushing up and an N2 pushing up and a mg pushing down. I'm just kind of hesitating here for just a second. I notice they don't really complete the free body diagram. They don't say that there's friction, but I think what they're trying to say here is to keep the cabinet stable. And they don't really give me a coefficient of friction. And I think, this could be better written because this force of friction would keep it from sliding. And of course, if the friction is quite a bit, it would be static friction. And what would happen is the cabinet would tilt if you push too hard there. And I think that's what they want to imply. If there was very little frictional force, like this cabinet was sitting like on a tile floor, there's a chance that this push would actually be unstable because it overcame the frictional force and it slid before it tilted. But we couldn't really answer the question that it's going to slide first because we don't have a coefficient of static friction. So again, I'm going to go with this idea that the cabinet, that this is a static problem. It's about rotation, that the cabinet here is, locked into place with enough frictional force that it's going to tilt and not slide. All right, so with that in mind, I will come back and set this one equal to 0. It may not be obvious then, but since we're not worrying about it sliding, we're not going to really need to worry about that force in the y direction. But I'm glad I brought it up for discussion. In fact, as long as I'm here, I'll bring up the forces in the x direction, that you would have the force you're getting pushed minus the static friction, and that would have to equal 0. That's why I am saying that this problem could be better written. This problem really should be discussing on whether or not it tilts first or does it slide first. And again, because of the lack of friction in the diagram and the lack of coefficient, I'm going to say that the author meant that we don't need to worry about the sliding part of it, the tilting. So, of course, then that was kind of a fun review, but really not helping me solve the problem. All right, so I'm going to jump to this torque and then put a pivot point maybe right here. Nah, maybe I should do it right here because I think you'll feel more comfortable right here. But we're back to what I said earlier. Once you get the idea of what the physics is going on and you have your physical picture and your free body diagram, now you're at step 3 to write out the equations. And part of writing out that equation is deciding where to put your origin and which way to orient it. And in this case, and in fact in all cases of statics, you put your origin anywhere, the torques have to be coming out to be 0. The logic being that it doesn't rotate around any point. So you pick any point you want, it's got to come out to be 0. That's why I could pick a point here and a point here. The good thing about picking this first one that I was about to is you'll see that you would get no torque from N1, and then the only thing in our equation would be N2, is what we're trying to solve for. So that's why I jumped to that one right away. But on the other hand, that might be confusing to students as they learn because it actually pivots around this point. So somebody's focus on the physics would say, don't you have to pick that point because that's what it pivots around? And I would say, well, no, it's true for every point, but it's easier to see this point. But sadly, when I pick this point, N2 is not going to be part of my equation. I'm only going to get an N1. But I can come back to this statement and then figure out what N2 is. And so I think maybe that's the best way to go with this one. So for your benefit, even though it's a little bit longer math, I'm going to pick my origin in a place that is not mathematically the best, but physically is the best. All right, so let me proceed then. So picking this to be my rotational point, I'm going to calculate the torques. And you can see then, and if we kind of review the equation for torque is R cross F, which means the magnitude, and these are vectors, would be the magnitude of R times the magnitude of F times the sine of the angle between R and F. And so when you look at all the forces involved, the ones that are right here at this origin, which would be N2, and for that matter also the frictional force that wasn't shown in the diagram, these two forces give you no torque because R is 0. And so the torque from N number 2, which by the way is the torque from the unlisted static frictional force, are each going to be 0. That's why I was saying that, I don't really like this origin mathematically because it knocks N2 right out of my equation. And so I can't solve for it. But it might give me enough information to solve for N1, which then I can use back here to get N2. And that's what I'm going to do here. Okay. So the torque from N2 is 0. Let me move on to this torque right here. So this torque, which is the force from gravity, has a perpendicular distance that's half the width of the object. And so let me give the second option for calculating torque. You can group these two together and call it the perpendicular distance from the line of action. So even though the force of gravity is right here at its center of mass, if I draw a line, that's its line of action with a perpendicular distance of half the width. So I would say then the torque from the center of mass would be 1/2 the width times mg, using that one. Okay, the torque, and maybe I should call it the magnitude of the torque. Let me not distinguish between positive and negative quite yet. Let's see, the torque from N number 1, using this idea of torque, and looking back at my diagram, I would have the distance of the whole width and then N1. So this would be a width and then N1. That would be the magnitude of that torque. And then coming over here, I kind of have the same thing. Here's the force, and instead of using this equation, I can put the R and sine theta together and get this line of action. So it would be this distance, which they call Y. And so the torque from our push would be Y times the F, and at least that would be the magnitude. All right, so I think I've covered all 5 forces. The 4 that your author lists here, the F, the N1, the N2, and the force of gravity. And I even mentioned the one that he's kind of leaving off here, the force of friction, but understandably, it doesn't contribute any torque. So these first two have 0 for torque, and then these have this magnitude. So if I come back up to this statement, and I say, let's add up all the torque, setting it equal to 0. And let's do our traditional clockwise is negative, counterclockwise is positive. So if I have this and kind of imagine putting my finger and pulling down with the force of gravity, that would tend to rotate this paper in a counterclockwise direction. So it's a positive torque. So I would say that the torque from the center of mass is a positive 1/2 W mg. And then number 2, N1, so our second torque from N number 1 here, would be, again, if you kind of hold it there and imagine me pulling up, so it would make the paper rotate like this. Okay, and so that's a clockwise rotation. So I'd say that's a negative torque. So negative width times N1. And then the last one, which is kind of a push on the cabinet this way, push on the cabinet this way. Again, that would rotate it clockwise. And clockwise is our negative direction, so that's a negative torque. So I would say that's a negative y. And, well, let me just put yf and set it equal to 0. And let me copy down the first two, because in the problem, they gave y as 1.25 times the width. So I'm going to go 1.25 times the width for the y. And for the force, they gave 0.242 mg. So 0.242 mgs. Okay, so notice that every term has a width in it, so I can factor it out and divide it by 0. Okay, this right here, this mg and this mg can be brought together. I'll just write it as 1/2 or 0.5 mg minus, and I'm going to put those together. So this would be 1.25 times 0.242, and that would be 0.3025 mg. And this one here I'm going to bring to the other side so that it's just N1. And so now I have 0.5 minus that last answer. And this would be then about 20%, so 0.200 mgs. Okay, so that's N1. Now remember, back here, the two of them have to add to 1 mg. So that means N2 has to be 80% of an mg. And that is the answer, 80%, or they got 80.3%. Yay! All right. Well, hope that was helpful too. Take care.